Hello everyone, welcome back to Sustainability and Engineering. I'm your host, Engineer Shahzad Sayeri. Today's session is one of the most important sessions in the entire CPD series because this topic decides whether your project moves smoothly or gets stuck in authority loops. Today we are talking about codes and standards in the UAE. NFPA, ASHRAE, CIBSE, British standards, European standards. Most engineers know these names. Very few engineers truly understand how they work together in real UAE projects. And that gap is where most rejections happen. By the end of this session, you will clearly understand what is code and what is a standard, why the UAE uses multiple international codes, where each code applies in MEP works, which authorities check what, and most importantly, how to design once and get approved once. This session is not academic. This is real-world authority engineering. Let's fix the foundation first. A code is mandatory. A standard is guidance. Let me repeat that. A code tells you what must be achieved, and a standard explains how to achieve it safely and correctly. In UAE, codes are enforceable, codes are contractual, codes are not non-negotiable, whereas standards become mandatory only when they are referenced by authorities, by project specifications, and by employer requirements. This is why arguments like, "but in my previous project," do not work in the authorities. Authorities don't approve experience, they approve written compliances. Now let's address a very common question. Why doesn't the UAE have one single code? Because the UAE construction is international, multinational, and multidisciplinary. Instead of reinventing engineering rules, the UAE adapts the best systems already proven worldwide, from the US, from the UK, from Europe. Then authorities apply local climate, safety, and operational filters. This approach ensures safety, consistency, and global credibility. Your role as an engineer is not to challenge this system. Your role is to align with it intelligently. Authorities do not design your system. They verify three things: safety, reliability, and compliance. They check whether your design protects occupants, performs during failure, can be maintained, and can be operated during emergencies. Authorities do not accept assumptions. They accept calculations, references, written justification. This is why authority engineering is a separate skill from pure design engineering. Let's start with fire. In UAE projects, fire engineering overrides everything else. If it affects life safety, NFPA dominates. NFPA governs firefighting systems, fire alarm systems, smoke management, fire pumps, means of egress. Civil defense does not care how elegant your HVAC design is if your firefighting strategy is weak. They assess worst case scenarios, pump redundancy, hydraulic margins, system survivability. NFPA is not optional. It is backbone of the life safety of UAE. This is where many engineers struggle. Common mistakes are undersized pumps, incorrect zoning, wrong hazard classification, incomplete interface with power and controls. Civil defense reviews drawings line by line against NFPA clauses. If something doesn't match, approval stops. Simple as that. Now let's move to comfort and performance. This is where engineering becomes something people can actually feel. This is where ASHRAE comes in. ASHRAE doesn't just deal with machines and numbers. It defines how a building feels to occupy. It answers very practical questions like, is the space too hot or too cold? Does the air feel fresh or stuffy? If the system is wasting energy or working efficiently in the background. In simple terms, ASHRAE defines how buildings feel to occupants, how buildings breathe through ventilation, how much energy they consume to stay comfortable. ASHRAE governs critical aspects such as thermal comfort, which involves the temperature, humidity, air movement, ventilation rates, that involves how much fresh air is actually required. Then indoor air quality, that involves controlling CO2, pollutants, and contaminants. And then finally, energy efficiency, which involves achieving comfort without unnecessary energy loss. And this is very important point to understand. A building can be fully fire safe, it can pass all fire life safety approvals, but it can still be uncomfortable to sit in, unhealthy to occupy long term, insufficient and expensive to operate. Fire code protects life during emergencies. ASHRAE protects everyday living and working conditions. That's why ASHRAE standards are essential. They ensure buildings are not just safe, but also comfortable, healthy, and sustainable for the people inside. And as an MEP engineer, this is where our real responsibility begins. Now let's talk about how ASHRAE and authorities are connected in real projects. Most authorities will not explicitly say, show me the ASHRAE clause number. But don't be mistaken, ASHRAE is very much present in their reviews. When authorities ask for things like pressure calculations, CO2 level justification, energy efficiency and compliance reports, what they are really asking is, have you designed the system according to ASHRAE principle? They may reference local codes, regulations or authority guidelines, but behind most of all those requirements, ASHRAE forms the technical backbone. Authorities want to be sure that occupants will receive enough fresh air, indoor air quality will remain healthy over time, and energy consumption is controlled and not excessive. And this is where the important decision comes in. ASHRAE is what separates a system from a system that simply works from a system that is properly engineered. Anyone can make a system run, but a well-designed system feels comfortable in all seasons, maintains healthy indoor air quality, and performs efficiently throughout its life cycle. So even when ASHRAE is not written on the checklist, it is still being indirectly followed. And engineers who understand this really struggle during the authority reviews because their designs already align with what authorities are looking for. Now let's talk about something that separates a calculator from an engineer, and that is engineering judgment. This is where CIBSE comes in. CIBSE is not just about rules or limits, it's about thinking like an engineer. CIBSE focuses on design philosophy that involves understanding the intent behind the system. System selection and logic that involves choosing the right solution, not just an acceptable one. And then engineering judgment that involves applying experience, context, and common sense. CIBSE helps you confidently answer questions that client, reviewers, and even your own team will ask. Why did you choose this system and not the other option? Why is this airflow rate appropriate for the space and usage? Why is this noise limit acceptable for comfort and function? These are not questions answered by minimum compliance, and that's the key difference. CIBSE is not about minimums. It doesn't ask what is the least I can do. It asks what is the most appropriate solution, what is robust over the building's life, what reflects good engineering practices. ASHRAE tells you what must be achieved, authority tells you what must be complied with. CIBSE teaches you how to think, so you can justify your decisions with confidence. That's why CIBSE represents design intelligence, and why engineers who follow it design systems that don't just pass reviews, but stand the test of time. Now let's understand when CIBSE truly becomes powerful in real engineering practice. CIBSE really matters when projects move beyond simple answers. It becomes critical when multiple technical solutions exist and more than one option can work. Optimization is required, not just compliance. Space is limited, and every millimeter, decibel, and watt matters. In these situations, rule of thumb engineering quickly reaches its limits. This is where CIBSE gives engineers an edge. CIBSE allows you to justify decisions logically, not emotionally or arbitrarily. Instead of saying this is how we usually do it, you can confidently explain. You can explain why one system performs better than another in this context, why a slightly higher capital cost may reduce long-term operational issues. and why airflow, noise levels, or control strategies were selected deliberately. CIBSE helps you design with intent, not guesswork, and this is important in professional reality. Senior engineers rely heavily on CIBSE because at senior level you are not judged on calculations alone, you are judged on decisions. On the other hand, junior engineers often ignore CIBSE, not because it's unimportant, but because it requires thinking, reading, and judgment, not just copying past details. And that's why many engineers struggle later in their careers. Those who adopt CIBSE early learn how to think critically, defend their designs in meetings, and gain trust from clients and authorities. Because in complex projects, good engineering is not about having one answer, it's about choosing the right one. Now let's step away from the drawings and calculations and move into site reality. This is where British Standards Institution, commonly known as British Standards PS, becomes critical. British standards are not about what you intended to design, they are about how the design is actually built. BS focuses heavily on installation methods that involves how systems are fixed, connected, and supported. Materials that involves what is accepted, durable, and proven. Testing procedures that involves pressure tests, leak tests, performance checks. And then workmanship quality that involves the standard of execution at site. In simple terms, British standards protects projects from very real site problems such as poor or shortcut installation, inconsistent execution across contractors or trades, premature failures that appear months or years after handover. And this is a key distinction every engineer must understand. Design approval is one thing. Drawings may be approved, calculations may be signed off, but site approval is another thing entirely. Authorities, consultants, and inspectors don't just look at what was designed, they look at how it was installed. British standards act as a bridge between design intent and site execution. They ensure that what was approved on paper is delivered with the same quality on site, because even the best design systems will fail if it is installed poorly. And that is why strong engineers don't stop at design. They use British standards to protect the projects, all the way from drawings to testing to final handover. Now let's focus on site inspections and testing and commissioning. This is where theory is tested against reality. During site works, inspectors and consultants closely observe activities such as pressure testing of pipe systems, system flushing and cleaning before commissioning, insulation checks for thickness, continuity, and workmanship. At this stage, discussions move away from drawings and calculations. What really matters is now how the system has been executed. This is where British Standards Institution, or simply BS references, become the primary benchmark. Consultants and inspectors rely heavily on British standards to verify that tests are carried out using the correct procedures, acceptance criteria are properly met, results are consistent, repeatable, and documented. And this is an uncomfortable truth in many projects. This is where many contractors fail, not because the design was wrong, not because approvals were missing, but because execution quality doesn't match the approved intent. Common issues include incomplete or rushed pressure test, improper flushing leading to debris and long-term system damage, poor insulation installation causing condensation and energy loss. British standards remove ambiguity. They clearly define how testing should be done and what acceptable looks like. So when a contractor says this is how we usually do it, inspectors respond with show compliance with applicable British standards. In short, design gets you approval, execution gets you accepted. And British standards sit right at the center of this process, ensuring systems are not just installed but tested, commissioned, and handed over correctly. Now let's shift focus from site execution to equipment itself. This is where European standards, commonly known as EN standards, come into play. Developed and maintained under the framework of European Committee for Standardization, European standards are all about product compliance. They do not ask, can this equipment work at site? They ask, has this product already been proven to work safely and reliably before it ever reaches the site? EN standards focuses on product performance. That does the selected equipment deliver what the manufacturer claims? It involves factory testing. Has it been tested under the control conditions? And it also has safety certification. Is it safe for the people, systems, and building? These standards are critical for components such as valves, dampers, pumps, fire-rated components including spoke and fire dampers. For these equipments, site testing is not enough. Their performance depends on factory control testing and certification. European standards ensure something very important. That is, what is tested in the factory is exactly what gets supplied and installed on site. This protects projects from unverified or lookalike products, inconsistent manufacturing quality, equipment that performs well on paper but fails in real operation. That is why authorities, consultants, and inspectors often ask for EN test reports, CE marking, third-party certification, because EN standards provides confidence that the product meets minimum safety and performance benchmarks. The installed equipment is not an experiment. In short, European standards protect the project before installation even begins. They ensure that when you install a component, you're not just trusting the supplier, you're trusting a tested, certified, and standard product. Now this brings us to material submittals, a stage many teams treat as paperwork, but experienced engineers know far more than that. It's far more than that. When consultants ask for data sheets, EN test certificates, or CE markings, they are not asking to fill files or slow the project down. They are asking for proof of performance. Under European standards, every critical component must demonstrate that it has been tested, it has been certified, it complies with the declared performance and safety criteria. A data sheet tells you what the manufacturer claims. A test certificate proves that it was actually tested and verified. A CE marking confirms compliances with applicable European derivatives at EN standards. Together, they create a chain of trust, from factory testing to consultant review to site installation, and this is why one rule applies across serious projects. No EN compliance, no material approval. Without EN compliance, performance cannot be verified, safety cannot be assured, and liability shifts back to the project team. That's why consultants and authorities are firm at this stage, because once material is installed, it's too late to ask whether it was truly compliant or not. So material submittals are not bureaucracy, they are technical evidence. They ensure that what gets installed on site is not just acceptable on paper, but tested, certified, and fit for purpose in reality. Now let's step back and look at the big picture. In real projects, standards don't work in isolation, they work together. In one single building, NFPA ensures life safety, protecting occupants during fire and emergency conditions. ASHRAE ensures comfort and efficiency, making sure the building is healthy, breathable, and energy conscious. CIBSE ensures intelligent design, helping engineers choose the right system and justify decisions. British standards ensures quality execution. Make sure what was designed is installed, tested, and commissioned correctly. European Committee for Standardization ensures product reliability, verifying the equipment is tested, certified, and fit for purpose. Each standard plays a different role, but none of them replace the other. And here's the critical insight many engineers miss. Authorities do not approve documents individually, they approve in alignment. They look for consistency between design intent, system selection, product compliance, installation quality, testing and commissioning results. If one piece is weak, the entire system is questioned. This is exactly where senior engineers stand out. Senior engineers don't just know standards, they understand how standards interact. They can connect fire life safety with comfort, balance efficiency with practicality, align design decisions with site execution, anticipate authority concerns before they arise. That's why senior engineers face fear rejections, resolve commence faster, and gain trust from authorities and clients alike. Because real engineering excellence is not about following one code, it's about bringing all of them together in one coherent solution. Let me be very clear here. This is one of the most important slides in the session. Most authority rejections, site issues, and redesign do not happen because engineers lack technical knowledge. They happen because of process failures. In real projects, most engineering rejections occurs due to first, mixing standards randomly. That means using parts of one code here and another code there without understanding how they align. Second, ignoring authority amendments. That means relying only on international standards and overlooking local authority regulations, addendums, and special conditions. Third is using outdated additions. That means applying old code version simply because that's what we used before. Fourth is copy-pasting details. Reusing drawing, that means reusing drawings and specifications without checking if they suit the current project system or authority. Fifth is designing in silos. Mechanical, electrical, fire, and architecture teams working independently instead of as one coordinated system. And this is the key point to remember. These are not engineering failures. The calculations may be correct. The systems may even work. These are process failures. Failures of coordination, failures of communication, failures of verification, and failures of engineering ownership. Senior engineers don't just design systems, they control the process. They check, are the correct standards being used together? They check, are authority requirements fully integrated? They also check, are drawings, calculations, and site works aligned? Because good engineering is not just about knowing the codes, it's about applying the right code in the right way at the right time. And when the process is strong, rejections reduce, projects move faster, and engineering teams gain credibility. Let's pause here. This is the most important key takeaway of the entire session. In the UAE, engineering excellence is not defined by calculations alone. You can size equipment perfectly. You can run flawless load calculations. You can design systems that work on paper. But that is only half the job. True engineering excellence in UAE is about compliances. Compliance with authorities, compliance with standards, compliance with processes, and compliance with site realities. It's about understanding what authorities expect, how standards are interpreted locally, and how design, product selections, and executions come together. Your technical skills are what get you hired. They prove you understand engineering fundamentals. But your authority understanding, how approvals work, how review happen, how comments are raised and closed, this is what makes you a senior. Senior engineers don't just design systems, they design systems that get approved but get built correctly and get handed over without any issues. So if you want to grow in UAE market, don't stop calculations. Don't stop at just calculations. Master compliance, master coordination, master the authority mindset. That is the difference between an engineer who does the work and an engineer who leads the work. So if this session helped you, like the video, share it with fellow engineers, subscribe to the channel, because every correct piece of information helps build safer, better, and more sustainable buildings. Thank you all, and I'll see you in the next CPD session.